Good afternoon, everyone. Apologies for the late start today. My name is Katrina Croft-Kastorf. I'm the Communications and Events Coordinator with the Melbourne Energy Institute. Thank you all for joining us today for this public lecture with Professor Ian Hiskens, Venner Professor of Engineering in the Department of Electrical Engineering and Computer Science. Welcome. Before we begin, I'd just like to acknowledge that today we're gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people, who have been custodians of this land for thousands of years, and we acknowledge and pay our respects to the elders past. For those tuning in today, we'd like to invite you to acknowledge the traditional custodians of the lands. Just a little bit of housekeeping for our online audience. If you have any questions for Professor Hiskens, please enter them into the Q&A box and not the chat. We'll have some time for Q&A from the online audience and the people in the room. Now, just to introduce our speaker for today, Professor Ian Hiskens from the University of Michigan.
Okay, well, welcome to those who are here and to the online. I don't know where the camera is, up there somewhere. Firstly, I'd just like to point out that this is not a great image of power systems. So hopefully things will look a little greener than all those, but I can keep going? Yes. Yeah, okay. But I guess in lots of people's minds, that is what they think of with regard to power systems. So it's not doing what it's supposed to do. Okay. Yeah, great. Thank you. So I'm on sabbatical this year. We flew over in August and did the usual quarantining and all that kind of stuff. But it's given me a chance to think about a few different topics to, oh, should I be speaking to this? Yeah, sorry. Think about a few different topics to what I would normally be thinking about. And so the presentation is kind of divided into two pieces. The first is a little more controversial, anyway, enough to get people excited about thinking about some of these topics. And then the second part is more kind of classic research. The first part is motivated. You probably noticed that we've had an election recently, and not just in election time, but there's a lot of talk about energy and power systems and renewables and batteries and all those fun things. So I wanted to spend a bit of time talking about that. So the first part is looking at energy storage, and that leads naturally into electric vehicles. But I also want to then talk about grid applications and things that need to be thought through with regard to bulk storage on the grid. So then I'll move into kind of my more researchy topic, grid forming, grid following, converters, modeling associated with that, give some little examples and some experiments. And so there's a sort of split between the two pieces. So I wanted to first mention, just open some of the thoughts about electric vehicles. So there's around 1 million passenger vehicles sold in Australia annually. They have a design life of about 10 years, and therefore we should anticipate that with electric vehicles, they're also going to have a life of about 10 years. Now, I've certainly heard some representatives of electric vehicles say that the batteries last much longer. But if I'm an electric vehicle company, why would I give something away for nothing? So if cars are designed for 10 years, then the batteries associated with those cars presumably will be designed for the same lifespan. The average mass of a lithium-ion battery pack per EV is about 400 kilograms. And moving to 100% electric vehicles will result over the years in something of the order, based on current day sales, of about 400,000 tonnes of batteries per year. There's currently no economic second life applications Used batteries are currently crushed up into what's nicely termed black mass, and there's currently no cost-effective process for recycling any of that black mass. There's certainly people who are exploring these things, and maybe in 10 years' time or down the track, there will be some available recycling processes. There may be economic second life applications. That's yet to be discovered. But what I wanted to point out is, given current knowledge, 400,000 tons of batteries are going to end up in the landfill each year. That's a lot of waste products, non-recyclable waste products. Okay, so that's one aspect to think about with electric vehicles. Thinking about, so that's the end of life. What about the beginning of life for batteries? So there's current shortages of raw materials associated with the electric vehicles. There's a shortage for lithium, and the price is skyrocketing for lithium. There are ongoing issues with sourcing cobalt. A lot of it comes out of the Congo, and a lot of it is not being ethically sourced. There's kind of an irony that we want our coffee beans to be ethically sourced, but the batteries that underpin the future of vehicle transport, no one's even mentioning the issues associated with ensuring that those who own the materials are being rewarded appropriately for that ownership. So there's those issues that we need to think about as well. And the last point that I'll make there is a bit controversial. I certainly haven't done the studies of this, but given current generation mix in Australia, where carbon-based coal and gas still dominate the electricity mix, then there's a good possibility that under certain conditions, nighttime with low wind, that electric vehicles are actually producing more carbon emissions than traditional vehicles. So one needs to think through those issues as well. If carbon is being burnt to produce electricity that powers the vehicles, together with the losses of getting that electricity from the source to the vehicles, when you think of all the carbon and losses and so forth, maybe electric vehicles are not the right technology yet. So anyway, these are just thoughts as I sit at the beach and randomly think through these things, some of the issues that I think are important that need to be talked about. Okay, and while I'm on the subject of electric vehicles, see, I ride a bicycle, so I don't have to be a proponent for electric vehicles. So cyclists always win, right? Anyway, electric vehicles are fine for around town, but they're not well suited for long distance travel. I live near Rockhampton, if you've ever heard of it. It's about 650 kilometres to Brisbane, where occasionally we travel. That's not possible with a charge even of the long range versions of electric vehicles. It is possible for gasoline powered vehicles. Did you know that when you drive into a petrol station, fill up the tank, the energy that's transferred into your petrol tank in the time that you're filling is equivalent to about 5 megawatts. That's a lot of power, right? But you don't sort of think about that. The equivalent, it takes about 5 minutes to deliver sufficient energy to drive about 700 kilometers. At least it does for our little car. The equivalent for electric vehicle, which are more efficient in the exchange of energy, conversion of energy, is about 1 megawatt. So if I want to charge my electric vehicle in about 5 minutes to drive 700 kilometers, then it's roughly 1 megawatt is the power, electricity power that's required to charge that vehicle. The fastest, the highest powered DC fast chargers that are available at the moment are 250 kilowatts. So a quarter of what's required to be equivalent. And keep in mind that fast charging, if you're dumping 250 kilowatts in, the battery life is curtailed quite significantly. So thinking about some of those issues as well. And then coincident charging of electric vehicles on distribution networks is a difficult, challenging task. And Nando will give a talk tomorrow, I think, on that very topic. So if electric vehicles, given their range, are really only useful around town, instead of dumping money into subsidizing the sales of electric vehicles, perhaps it would be better to invest more in public transport. And if the majority of vehicles are only being driven 40 kilometers a day around town to get from home into the office and back, wouldn't it be better to put more into public transport to get the vehicles off the road rather than encourage more? And for those of us who live in the country, or in fact just want to visit the country, range anxiety is a real thing. If you're going out to some national park, you're not going to find too many charging stations in the national park. So I'd like to propose that a short-term solution is to think about plug-in hybrid electric vehicles so that you get the best of both worlds, that when you're doing short journeys, you can do so on battery power, but when you want to go long distances, you have the backup availability of the internal combustion engine. And I'd like to also suggest that in the longer term, that fuel cell-based vehicles, hydrogen-powered fuel cell vehicles, seem to offer a kind of a more sustainable outcome in the long term. However, storage of hydrogen is not a simple process. Okay, so let me move on to away from electric vehicles to thinking about renewable generation a little bit. And then we'll see the connection later soon back into the second half of the talk. So renewable generation, solar farms require about 1.5 hectares to produce 1 megawatt of electricity. So a 1,000 megawatt solar farm is going to take up about 15 square kilometers of land. Now, Australia has a lot of land, but if we're going to go fully renewable, we're going to need a lot of land. Wind farms require about 20 hectares to produce 1 megawatt of electricity. So again, if you're thinking about 1,000 megawatts of wind generation, that's a lot of land. And keep in mind that to make wind farms effective, you need to chop down all the trees. This is already becoming quite an issue in the Atherton tablelands, inland from Cairns, where the environmental groups were very happy when people started thinking about, or started proposing wind farms on the Atherton tablelands. They now have wind farms and they're very unhappy with what's been done to the environment there. Not just above ground, but underground, there's 600 cubic meters of concrete for every tower. And just to keep in mind, wind turbines are large mechanical devices that are exposed to the environment. Wind gusts transfer that torque impulse to the gearboxes, and it's not uncommon for the gearboxes to fail in wind turbines. And just to add to all of that, as I mentioned earlier, when we were looking at the picture of the transmission towers, significant new transmission will be required to support the renewable generation. Large areas of land will be required. They will be longer distances from population base, so that will require new transmission. Just the nature of variability associated with solar and with wind means that if the wind is not blowing in the south, presumably you might be able to get energy availability from somewhere else. And so the flexibility requirements will also mean greater amount of transmission and meshing of transmission as well. So the brave new world of renewable generation means more transmission. And people don't like transmission in their backyard. There's a great acronym, BANANA. Anyone heard of the acronym BANANA? Build almost nothing, absolutely nowhere. Actually, I can't remember it. That's embarrassing, isn't it? It'll come back to me, but it's build, anyway, whatever. I'll think about this, and during question time, it will come back to me. Build almost nothing anywhere near anything, something like that. Okay, so I've put a plot there, which I just pulled off the web the other day, and this is a continually updating source of information. So if you're interested, just go to this website here, and it just plots out in almost real time what the energy mix is for the Australian NEM. And so this was just the other day. The thing that's of interest I wanted to point out, well, there's a few things to point out. Obviously, coal, which is the black, brown coal is the lower brown part, the creamy colors are gas, blue's hydro, green is wind, and yellow is solar. And you can see, of course, that there's only solar during the day. You can see that there is a reasonable amount of wind, but nowhere near satisfying the energy requirements. But when you take a look at that and think, okay, if we're going to supply electricity at night time when there's no solar availability, how much electricity is required after dark? So based on this, the 13 hours of darkness from sunset to sunrise on Tuesday, I think it was, Australia used about 300 gigawatt hours of energy from 6 at night, maybe 5 at night to 6 in the morning. So 13 hours of span. So 300 gigawatt hours has to be solar free. There's no solar power available in the nighttime, unless you're starting to think of solar thermal, and that's not really, the economics don't really line up at the moment. Okay, so we need to think about bulk energy storage. So as I mentioned, about 300 gigawatt hours of energy was consumed the other day from sunset to the following sunrise. That number is going to grow significantly when you start to consider the electrification of everything. That's very much a push, right? So cooking, which is gas, in lots of cases will become electric. Heating, which is gas, will move to electric. So that number of 300 gigawatt hours is only going to grow. If we think about charging electric vehicles overnight, likewise, that's adding to that number. And that number is not any kind of peak day. That was just an average day the other day. The peaks are, of course, much higher. So where's that energy going to come from? Well, solar is a natural source, but it's only available during the day. So presumably there's going to be a lot of storage that's required. Let's assume that of that 300 gigawatt hours, just half of it comes from, half comes from solar, half comes from wind. That's a reasonable assumption, maybe. So that means 150 gigawatt hours of solar PV has to be generated during the day and stored for nighttime. That's equivalent to about 1,500 Hornsdale big batteries, the battery that's over in South Australia. It's not that big anymore, but that's about the size of it. And keep in mind, all of these batteries that would potentially be used for grid storage are going to need to be replaced after 10 to 15 years. Okay, batteries have a finite life. And once they're done, they become that black mass and get dumped in the landfill. What's going to make up the remainder? Well, probably or possibly wind is going to be a significant contribution to that. When looking at the other day, of that 300 gigawatt hours through the night time, 32 gigawatt hours was wind. So there's a good start. We're 10% of the way there in that sense. So maybe wind will make up the difference, but solar is certainly appealing in the sense of no mechanical parts for the future. So we need some bulk storage, and pumped hydro storage seems to offer a more sustainable solution than batteries. Pumped hydro storage has a lifespan of up to about 80 years or so. There's an investment in the infrastructure, but that investment is long-term. I'll just point to two projects or potential projects. So the one on the left is Barumba pumped hydro. It's proposed. It's in the early stage of meeting with the community and talking about what it offers. I can't really, I won't do the pointer thing, but there's a high reservoir and there's a low reservoir. And during the day, the red arrow points to the low point, and water gets pumped from there up into the high storage. And then during the night, well, yeah, when you need that energy, then it runs in the opposite direction from the high storage down to the low storage. This Barumba possibility has a power rating of 1,500 megawatts and energy storage of 30 gigawatt hours. So there's 10% of the required energy already. So that's a good start. Of course, this is early days, and to build the dams that are required will take an enormous amount of time to get the appropriate environmental permitting if it's allowed to go ahead, and then to actually build the infrastructure. Oh, and most of this is a national park or a large park. So how do you get the transmission in and out to it as well? On the right-hand side is what's called Kidston pumped hydro. It's actually under construction, and it's really innovative in that it's an old gold mine which had two pits associated with it, open cut and two pits. And there are different heights. And so the idea is to fill these things with water and pump water from the low one up to the high one where you've got available energy and run it back downhill. There's no environmental issues because it's an old mine. It already had, the environment's already been damaged, so let's use it for something else. Mind you, you would not want to drink the water that's being pumped up and down here. It's toxic. The power rating of this installation will be 250 megawatts. Its energy storage is 2 gigawatt hours. They're big numbers, but they're not big enough. There's still more that needs to be done. Okay, so I want to conclude the first part just by saying I believe power systems will never be 100% inverter based. Now you hear talk about, oh, we're moving towards phasing out all synchronous machines. Well, I think the best form of, the most environmentally friendly form of storage is pumped hydro, which is reliant on synchronous machines. Though there are other types of machines that you can buy from some of the vendors called doubly fed induction generators, but still there's going to be a lot of synchronous machines based on more traditional technology. Inverter, if we have synchronous machines, then the inverter-based resources need to be able to interact with them nicely. The different types of devices have vastly different dynamic characteristics, and they need to be able to work together. For example, the damping of inter-machine and inter-area modal oscillations relies on what are called power system stabilizers, a feedback loop that is vital for making synchronous machines remain stable on the grid. the tuning of power system stabilizers, the damping that's provided from them, is dependent upon a phase shift that compensates for a phase lag through the grid. So the power system is actually part of the feedback process. And as that power system changes, the phase associated with that power system, or the characteristics of the power system, change as well, making it very difficult to tune power system stabilizers across a wide range of network conditions. And when you think about wide range, what could be wider than having 150, well, gigawatts of solar during the day and 0 solar at night, and other such variations. So it's a difficult control design process, to be able to guarantee that the power systems will remain appropriately damped under the wide range of possible operating conditions. Okay, so that's sort of the end of this overview, if you like. What I will move on to next is looking more at details of inverter controls. But I thought we could take a break here, see if there are any questions or comments, and then move on. So take a few minutes to explore these earlier topics a little further.
So if we have large-scale EV adoption, but strongly encourage workplace charging during the day, you can solve the solar problem and storage.
So it helps deal with the demand associated with the vehicle charging. It doesn't help deal with all of the other 300 gigawatt hours that's already there. So things don't get worse in the nighttime. But it also has the other benefit that at the moment in the Australian national market, there's a tendency for prices to go negative during the day because it's often so much solar, and charging vehicles at that time would certainly be desirable. Giving the energy away would be desirable.
But if you do V2G, would that also help you at night?
So if you do V2G, so that's going to give you some of that. But again, if you think about the 300 gigawatt hours that's required, it's not going to give you much. And the other aspect is the more cycling you do on batteries, the shorter their lifespan. And so vehicle manufacturers have been reticent to move in that direction, because they're giving a warranty on something that they then lose control of. If the battery's only being used for driving that vehicle, then they're willing to accept the consequences of driving patterns. But if then you're using it for doing other things, they're not so willing to accept that. Yeah.
Yeah, Ian. So, you're giving us quite a somewhat bleaker picture of some of the battery economics, but nothing I haven't sort of heard before. I think it's worthwhile reminding people to get really excited and look at the downside. The point you made though on the we won't have any inverter based, we won't have 100% inverter based systems. What you're actually saying, I think, is you won't have 100%. What are you saying? So you still can see a lot of wind and solar, but you're saying it's going to be still matched with synchronous machines in the form of pumped hydro.
Yes.
So there's still inverter-based renewables there.
Oh, absolutely.
So,
yes.
So, yeah.
Yes.
Do you see a situation where you say, well, actually, rather than inverting the wind and solar, why not rectify the synchronous machines and get them to output DC?
Yeah, I don't think so. In terms of the synchronous machines, like I mentioned, there's a vendor that is happy to sell you large reversible motor generator sets that are based on doubly fed induction generator technology. And with doubly fed induction machine technology, the interface with the grid is inverter based. And so from that point of view, if people moved in that direction, yes, you could do away with all of the synchronous machine. But the doubly fed versions are more expensive. They offer more controllability. So in the traditional pumped hydro, it's on or it's off. In terms of pumping, that is, it's either pumping flat out or not at all. There's controllability with generating, but not pumping. The doubly fed version gives you finer control, and that's beneficial because, you know, as the solar and the wind varies, you'd like to match what your pumping load is to that availability. So it might be that the economics in the longer term lead to doubly fed being the standard technology. And then my hypothesis about synchronous machines goes away. Having said that, there's a lot of investment in places like Snowy that's not about to go away. And that's synchronous machines. In terms of run-of-river hydro, synchronous machines are still the way to go. And so if hydro becomes an increasing part of the mix, then there will be synchronous machines associated with that. Of course, dams are not seen as being environmentally friendly. So the whole concept of hydro is questionable in itself, but which is better, dams or 1 million tons of black mass? Anyway, per year. Yeah.
Answer this question. When I grew up, we used to actually have our calculator put in the battery and it start working. I was absolutely amazed that later we don't need that. Somehow there is light and maybe turn on the light, sunlight, and then the calculator is working without any battery. That was a very clever invention. And I'm very interested whether you are aware in this world any kind of new invention that individual at home or can produce, particularly from the sun, that we can store the energy and make use of it, either individually or in the home. Whether you are aware of any such kind of invention.
So you know, in the calculator, there's tiny little solar cells, and that's what's producing the power. And the technology is not dissimilar to the large scale solar photovoltaic. So there are other forms of storage. There's a supercapacitor storage. There's phase transition types of storage. There's flow batteries. You know, I've only kind of talked about lithium-ion batteries, but there's technology called flow batteries that possibly play a more sensible role in a grid environment than lithium-ion batteries. So there's different battery technologies that may become viable. But you know, when you're dealing with energy, you need to put it somewhere, and that's a mechanical process or a chemical process. But so I'm not familiar with. I mean, I'm sure there are other forms of storage and conversion and so forth, but not to the extent that's required.
Okay, thank you. Thank you. We'll, hopefully there will be some kind of invention.
Yeah.
Hopefully.
Okay, so maybe we should move on to the next part. So it gets a bit boring from this point onwards. It's just sort of researchy stuff. But again, on sabbatical, I have an opportunity to kind of think about different topics. And one of the topics that is fundamentally important for moving the grid towards carbon or decarbonising the grid are the grid forming or grid following inverters. So when we think about solar photovoltaic, it's producing electricity as DC, and that DC needs to be converted to AC. Inverters do that. We think about wind turbines, most of them are doubly fed induction generators. The rest tend to be synchronous machines, but they basically all build on having inverters to do some part of the conversion process to connect to the grid. So from the rooftop solar through to think about the largest wind turbine or the largest batteries that are around. They're using inverters, and there's these two different control strategies called grid following and grid forming. And it seems about 98% of the inverters that are used are grid following. And so these two figures that I've got up the top here, I stole from this paper. There's an enormous amount written about this topic of grid forming and grid following. When I talk with industry people, they see things differently to a lot of what's published in the literature. And for every definition, there's an equal and opposite definition associated with some of these things. But this particular paper I found really quite enlightening in terms of clarifying some of these things. So grid forming on this side, the sort of fundamental difference between these two types is highlighted in red. Grid forming, actually, let me talk about this is what you find most used on the grid currently. It's called grid following. It has what's called a phase lock loop associated with it. So it measures the voltage and based on this phase lock loop, estimates the frequency, which fuses that through a current controller to control the voltage to to deliver the appropriate amount of power to the grid. I'll come back to this phase lock loop. Grid forming, which are very few around, but offer a lot of benefits. They don't have a phase lock loop typically. They utilize this thing called frequency droop, such that the power is measured, the power being delivered to the grid is measured. It's compared against a set point value that generates through the frequency droop a frequency, which is then fed through voltage control to regulate the voltage and achieve the desired outcome. What's meant by a phase lock loop? Well, this little block down here describes conceptually at least what a phase lock loop does. There's measurement of a signal and it's compared with an internally generated oscillator signal. And it's compared in the sense of the phase comparison. So if you think of this as an AC waveform, and think of this as a different AC waveform, what this phase comparison is doing is looking at the different points where the peaks occur. So this is an AC and has a peak over here. This is an AC waveform, it has a peak over here. They're different. That error signal is fed through a proportional integral controller to adjust a voltage controlled oscillator. An oscillator alters the phase here to achieve a better match with that phase there. That's generally what's going on in a phase lock loop. The outcome is that the phase of the internal signal matches the phase of the measured signal. So I end up with an internal waveform that's in phase with the measured value, and the frequencies match as well. So out of that, there's a measured voltage is measured, it's passed through this thing. that produces, actually all of that is encapsulated in this block here, because the frequency gives rise to the phase. That's what's being checked in that. And that's then used the rest of the control loop. Okay, so that's the traditional form of grid forming and grid following. So what we did a bunch of years back was, before anyone had thought about these categorization, was to develop a control strategy that involved both a phase lock loop and a frequency group. And when I talk with people in industry and academia, it's like, well, and I say, is this grid forming or grid following? Because it invokes both pieces. It's like, it doesn't seem to fit. So anyway, this is our particular control scheme, and I'll come back to various aspects of it, but there's a measurement of the terminal voltage similar to grid following, a phase lock loop, which gives rise to the frequency and angle similar to grid following, but that then feeds through a group characteristics to give it power. In the grid forming, the power feeds through group to give the frequency. In our case, the frequency gives rise to the power set point. Then there's an active power controller, and that drives the voltage here to give rise to the desired outcome. So it's a hybrid form of control. It takes both aspects into account. So one of the questions that arises is, if the phase lock loop is locking on to a measured signal, how can I start our control strategy in what's called a black start? Black start means there is no AC system available, and I want to start this thing. Think of out in the wilderness, there's no grid, but I have one of these controllers. How do I power the house based on this? There's nothing there. I need to start it somewhere. So this is the sequence for starting this up. So there's a circuit breaker, connects to either the grid or whatever the load that's being supplied. So with the circuit breaker open, I energize the power electronic inverter using some fixed frequency. So for the initial phase, this initial part of the process, I'm just energizing the inverter up there. It's connected to a filter. So where you see that L sub F, that's the inductor and its capacitor, it's connected to a filter. So when I energize the inverter, it's going to energize the filter, it's going to apply a voltage where the point V sub T is. So I'll energize the filter. I have a voltage there. Now I can synchronize the phase lock loop onto that existing voltage and switch from the fixed frequency onto the frequency of the PLL. So I've now turned on the PLL. It's still disconnected. The circuit breaker is still open, but I'm just going through a startup process to be able to get the PLL synchronized to something. Okay, now everything's ready to go. I can close the circuit breaker, and I'm now energizing the grid or connecting to the grid. So if it's a black start, there's no load there. I close the circuit breaker and the converter starts to supply the load of the house or whatever it might be. And that's what that's saying. If, however, I'm connecting to a grid that's already energized, then there's a slight modification that's required, and that's what is to use what's called a synchronism or synchro check relay, which says I can only close that circuit breaker when the voltage on either side of it matches. And so I can control the phase lock loop to adjust the voltage to achieve the match, close the circuit breaker when there's no voltage drop across it, and I'm then synchronized onto the grid. So the startup process is quite straightforward, and that addresses one of the issues. There's some details, and I'm not sure how much people are interested in those details, but in terms of modeling behavior, it's important to think about what's called this rotating reference frame idea. And a nice analogy to think of that is to think of a synchronous machine. Okay, we're not dealing with a synchronous machine when we're thinking about inverters, but if you're thinking of a synchronous machine, then you can think of the rotor that's spinning. And if you think of that spinning, then you can put a line on that, and that becomes a reference, and that reference is rotating. And if I kind of sit on that line and rotate with it, then I don't see the rotor spinning anymore. I'm moving with it. And so it's the same thing with these rotating reference frames, that the voltages that are being applied to the inverter, it's an AC waveform, but you can think of that AC waveform in terms of sort of a voltage vector. I'm not exactly sure the best way to explain it, but that is rotating, continually rotating. So the voltage, in a sense, is rotating, and then I establish the reference frame to rotate with that voltage. And when I do that, AC waveforms look like constant values because I'm traveling with the waveform and I'm seeing things as constants. And then I can design a control loop based on those constant values. So I use my rotating reference frame to go from true AC waveforms to something that's equivalent but constant like DC, do my control manipulation, and then convert back in the opposite. So you then go from my rotating reference frame back to the reality, and that gives me an appropriate voltage waveform synthesized using a control loop that hasn't had to worry about the AC nature of the waveforms. It gets a little bit complicated there. I guess one of the important things I wanted to mention is across an entire grid, one has a global rotating reference frame, and I use the capitals DQ, stands for directing quadrature, but that's not important. And then each device, like an inverter, like synchronous machine, has a local rotating reference frame associated with it as well. So for every device, I have this rotating reference frame. The slide that's coming up looks at how to rationalize, how to connect between the two. But the important thing is that with this rotating reference frame, it turns AC signals effectively into constants that I can then manipulate in the control strategy. Okay, gets a bit messy. I won't spend too much time on all of these details, but the active power dynamics initiate with the phase lock loop, as we saw in the diagram before. And the dynamics of the phase lock loop are really looking at this angle difference here. And they're saying, I want to bring this is the D axis of my rotating reference frame. I want to align that with the terminal voltage. And so, back when we were looking at phase lock loop, it's about aligning the phase of two signals, an internal signal and a measured signal. So this is the measured signal, and then we're wanting to align this back to that. So the angle difference between those two is this minus that. And that's what's going on there. It's fed through a proportional plus integral controller to establish frequency. And that frequency is then used to establish the angle of the phase lock loop. So that drives the dynamics. This last equation is related to the difference in the rotational speed between the capital DQ frame and the lowercase dq frame is going shown up there. That difference gives rise to the change in that angle. And then, as I mentioned, driving this angle difference to 0 is equivalent to aligning this d-axis with the terminal voltage as well. Oops. And then, so that's the phase lock loop. And then we have this group characteristic. As I mentioned before, it involves active power and it involves frequency. So in traditional grid following, the frequency is measured to determine the power. In the traditional grid forming, the power difference drives the frequency. In our case, the frequency obtained from the PLL drives the power difference. And then that power is used down here to drive the angle, which is this angle here. And that is effectively the angle across the filter inductance. So that's really sort of the control strategy. It's actually quite simple. It looks complicated in the diagram up there, but it's not too complicated. I won't go into details. That's the process for comparing or changing between different reference frames. One of the things I will mention is dynamic line modeling. So in traditional power system dynamics, the rate of change of the states is relatively slow compared with the fast dynamics of the inductance and capacitance of the transmission line. When it comes to looking at inverter-based sources, the control loops are much faster. And it's been observed in industry that there can be an interaction between the dynamics of the network inductance and capacitance and the dynamics of the inverter controls. And so there's a need to think through the modeling associated with dynamic lines. And so this just kind of gives a very brief overview of that. If we just think of an RL branch, so a series connection of a resistor and an inductor, then we can write that top equation. It's a three-phase, the vectors capture A, B, and C phase, and that's just time domain. But then we can convert that time domain using a DQ rotating reference equation, like here, and we end up with a model that looks like that. So there's actually a dot on top here. It's the derivatives of those terms give rise to this model. Okay, so that captures our line dynamics. What does the steady state of the line dynamics look like? So we can do a little bit of analysis. And the really cool thing that comes out of this is that even though we're modeling the line in much more detail, if we think carefully through the steady state outcome of that, we recover what's called the traditional phasor analysis. Almost. In the case of normal phasors, the frequency that appears is the nominal frequency. So 50 hertz, 2 pi times 50 radians per second in the Australian context would be the number that you put in there. When you go back to basics and think through the steady state idea, it turns out that the right value for frequency that you should put there is the steady state value. And it might be that the steady state value is actually 50 hertz, but the steady state, if there's some disturbance, it might actually be 49.9 hertz. Not a big difference, but if you're trying to kind of rationalize the various different models, it might be enough to make a difference. So this frequency should actually correspond to the steady state, not the nominal frequency. So moving on and looking at how does this all behave. So the initial case is to put one of these inverters onto a Thevenin equivalent. So I take my large network and replace it by a source in series with an impedance, and then look at how does the system behave given a step change in the desired value for output power. And for the first case, it's varying the impedance of the network, actually varying the inductance of the network, but it's kind of the same thing. And what we see is when we have a weak network, the response is kind of slow. When we have a stronger network, the response is much faster. And that's actually sort of what's observed in industry as well.
Sorry, Ian, is that a response to a contingency or this is a black start? I missed something.
So this is just saying I'm starting at 0.5 per unit and doing a step change in output power up to 0.7
The whole,
of the inverter output. Does that make sense?
Yeah.
And so is the plot on the left the grid forming control, or the plot on the left, is it the grid forming or the grid following control?
Yeah, so the plot on the plot on the left is this is all for my hybrid controller. And when we go back to jump back to this point here. So this parameter, this group parameter MP, when it's equal to 0, then the power is constant, and that corresponds to a grid following type of situation where there's no droop associated with the grid following. When this is not constant, not 0, so a positive value, then this gives rise, this is equivalent to grid forming. So as that value for MP gets smaller and smaller, the characteristics become more and more like grid following. And as it becomes larger, it becomes more like grid forming. So in this case, in all of these cases, MP is equal to 100. So it's effectively grid forming in those cases. On this side, I varied the value for MP from 0. So this oscillatory case is effectively grid following through to having a large, very large value for MP, which gives grid forming. And you can see that that MP is actually affecting the damping. So when it's 0, you have this very low damped oscillation. And as you make that larger and larger, you see over damping happening.
These are all local oscillations, right? It's nothing to do with what the rest of the grid's doing. This is
Correct.
just
This is
the control system itself behaving.
Yeah, so you've got this inverter and it's just injecting a power that's oscillating. At the other end of that line, it's an infinite bus, and it can just take whatever is being produced. I then looked at a case where I put 2 of these inverters at the same location and then did some weighting of them by a factor of alpha, multiplying the grid forming character, multiplying, making one of those look like grid forming and one look like grid following. The grid forming one I multiplied by alpha and 1 minus alpha for the other, so you get this convex combination of the 2. And then looked at how these 2 things behave. And so for the solid line is with a much stronger system, and the dashed line is a weaker system. So with a strong system, they both behave very similarly to each other. Under weaker conditions, the grid forming shows this kind of poor, over-damped behavior, and the grid following is oscillatory, as we saw before. So in this case, they're both operating at the same location and exhibiting different characteristics. So that was for varying the strength of the network. And then I just chose the weak network and looked at the composition between the 2 by varying this alpha So for the dashed lines, the grid forming and grid following have equal weighting in the impact. And in fact, that dashed line there corresponds exactly with that there. But then the comparison is with the solid line, which is more grid following. And so you can see it's way more oscillatory. You've lost that damping associated with the grid forming characteristic. The next experiment we did, and the last one that I'll talk about, was to set this up as a microgrid. So with 2 inverters, 2 loads, circuit breaker connected to the grid. The first thing was to look at the eigenvalues of that network. And sure enough, what we find are some very fast eigenvalues associated with the line dynamics and with the filter dynamics of the 2 inverters. And then the eigenvalues that are of interest from a control perspective are these guys down here. So you get this quite a wide range of eigenvalues, line dynamics very fast here and out here. Then there's some filter dynamics and then the control sitting in there. So in this particular case, at least, we didn't see a whole lot of interaction between the lines and the filters and the controls, but certainly in practice, people have seen some of those interactions. In terms of the dynamics of this, we opened the circuit breaker and then let things settle and then close the circuit breaker. And I won't, again, for sake of time, I won't go into all the different plots, but you can see, so the top one is active power generated by the inverters. The circuit breaker opens at 1 second. There's power being drawn from the grid, so that has to be made up by the inverters, so they jump up. And then when the circuit breaker closes again, power drops down and then recovers back. And you can kind of work through all the others and it all sort of makes sense what they're doing. So the last slide I'll show is this control scheme. We published it back in 2008. And I had a student actually build this in a lab. I'm not a lab person. I wouldn't know which side of a lab to walk into. But anyway, the student was able to get things working. And so this is from a paper a long time ago. But the interesting thing is back then, no one was interested. And so we did this work and we built these things and published a couple of papers and moved on because there was zero interest from the community. And now everyone's kind of into this sort of thing. But this is a representation of a physical microgrid that we physically built in the lab. And the starting condition is that the circuit breaker is open. So this is initially operating as an island microgrid. So that's this phase here, and it's drawing power that much. There's no power being drawn from the grid. That's the blue. And then at this point, the circuit breaker is closed, draws power from the grid, the power being supplied from the 2 inverter-based devices drops down, and then here the breaker opens again. Grid power drops off these summer. So that's the power on that side, the frequency of the grid. So it's doing, it's isolated initially. So the frequency is down 59.8. And at this point, it connects to the grid. It's a 60 hertz system in the US. So it follows grid frequency. And then the switch is open again and it drops back to its own, the value of frequency that keeps everything balanced. So those experiments from more, 14 years ago or something like that. Okay, so in conclusion, this this hybrid inverter control scheme kind of incorporates a bit of both the droop and the phase lock loop. So it takes on characteristics of both grid forming and grid following, and it achieves robust operation over a wide range of system conditions. I guess the more sort of important aspect of the conclusions is there's much to be discovered still. What's the impact of inverter-based resources on the modal oscillations that are set up between large generators, large synchronous machines across the grid? How do those modal oscillations evolve when there's massive changes in inverter-based generation that's happening? What's the role of the network in sustaining or destabilizing oscillations? How does the network interact with the inverters, or can it, or under what conditions can it interact to lead to bad behavior? How does one go about modeling tens of thousands of rooftop devices in a way that you capture the kind of aggregate corporate overall dynamic behavior that's going to affect the 1,000 megawatt wind farm, that solar wind farm, or the 1,500 megawatt pump storage scheme? How do all of these tiny little rooftop settings, when aggregated together, impact on the overall grid? The concept, the idea of load modeling has been a kind of perennial issue for utilities forever. How to model the loads in a way that sort of makes sense from a dynamic perspective. Add to that, it's not just the loads anymore, it's all of the small distributed energy sources that are across the grid. How do they collectively impact behavior? Lots to be discovered. Definitely more sabbaticals required. Okay, thank you.
Thank you, everybody, for joining us today who's here, and also to our audience online. And once again, thank you, Professor Ian Hiskens.
Okay.